Hi and welcome to Programming Percy, and today we will be talking about generics in Go. Generics was released in Go 1.18, and if you are interested in the other changes that was released in Go 1.18, feel free to view my video of that. Many people find generics a bit tricky and complex, but we're going to uncover the mystery. They are not that hard once you get familiar with them, and they can really help out in a codebase. So generics are a way of allowing a function or type to accept multiple data types by using a constraint on these data types. We will be looking more at how very soon. So to show you why we need generics, I've prepared a small case, and it's a subtraction case. So we have a few integers, I have a few floats, and I want to subtract values. As easy as that. So what I would regularly do is create a subtract method which accepts the integers and outputs the result after subtracting them. But this would not work for my floats. So one way to solve it is to basically convert the data type into integers, which is bad since we will round up and we will get not the correct result. So that's not a solution really. But it's possible sometimes to use a type switch to kind of check if it's an integer or if it's a float, and you could return that data type. But it's clunky. So the other way to solve it is simply by duplicating the code, but this time we will accept floats. And as you can imagine, this can grow into quite a few functions, and it's not really nice. So what if we could skip all these duplicate functions, or the typecasting, or the type switching, or the conversion of data types? What if we could use one and the same function? And that's what generics allows us to do. So let's take a look at how. Let's dive in and learn the basic usage of generics. We will be taking the subtract function and applying generic features to it, and whilst we do that we will learn how and why we do things. So I'm going to start with the very fundamentals of the Go language, and I will show you this because it's good to think about, and it's actually what a function parameter is. And when we say function parameter, what I mean. So a function parameter is the thing we add at the function declaration, and it's the data type and the name of the data type that we insert. And we define function params by using, so we do func, and we have our func name, right? And what we place in the parentheses is the function parameter, and the syntax is that we specify the name and the data type. And understanding function parameters is trivial, but it's good to keep in mind, because now that we are learning generics, we will use something called a type parameter, and it works in exactly the same way as function parameters. You specify the name of the parameter and the data type. So let's also mention that type parameters are specified by using brackets. So instead of the parentheses, right in front of the parentheses, in front of the function parameters that is, you add the type parameters by applying brackets. And let's go ahead and do this for the subtract method, because we want this to become generic. And we will basically define a data type that can be used inside the local scope of this subtract function. And let's go ahead and do this, and we will call this capital V. I suggest using capital letters in the generics because that's what I've seen others do. It seems to be kind of idiomatic for Go. Just so the eye will easily spot that this is the generic data type. And let's say that int is the data type that our type parameter accepts. So we have said that there is a data type called v, and it can be an integer. So what we can do, we can go inside the function parameter and remove int, and instead say that this is of the data type capital V. And we do the same for the results, that we will output capital V. Now let's go also ahead and remove subtract float 32 because we no longer need that. Now you might think that we have done nothing. We have accomplished nothing here. And you're right, and this won't compile because having an integer is actually not enough. Now I know I said that this is the data type. What this is actually the constraint. So what we put here is a type constraint. So basically we're saying we have the v and it has to follow or conform to the type constraint. And the type constraint is a interface, and it has to be an interface. So passing in int won't work because int is a data type, not an interface. But this is what we want to do. So just remember, whenever you pass a single value in, it has to be an interface or multiple data types. So what we do is that we add a pipe. Now the pipe sign actually says it has to be an integer or a float 32. And this works because we now only not have a data type, we actually have two data types delimited by the pipe, which says it has to be an integer or a float 32. Now this becomes a constraint. So for those of you who really want to know, that pipe actually is shorthand for creating a inline interface. So we are creating an interface here, but an anonymous one. So v can be either ints and floats, and we are using that to specify that a and b will be any of these ones, and we will return v. It's important to remember that you cannot insert a integer and b as a float. It has to be the same data types. You cannot mix them, not the way we currently have it. So we have a type constraint. We can actually, for the fun of it, go ahead and try this, and hopefully we will see it running smoothly. And if I go ahead and run this, you can see it prints on both, but let's go ahead and remove this because I noticed we are still converting to integers. So remove that, and you can see we're using the same function both for the integers and for the floats. So go ahead and run it again, and you should now see the correct results. How amazing is that? And how easy is that? It's not hard at all. One thing more about this is you can break out the constraint. Remember I said this was an interface? You can pass in any interface. Any. So let's go ahead and actually create an interface called subtractable. And it's an interface, and in here we pass in integers, we allow any integers, and imagine if we were to have a function for all of these, but we don't need anymore because we can simply reuse the same function for all of them. So we have created our subtractable interface, which defines all the data types that I want to support. Now what we can do is we can go here to the type parameter and change the type constraint. Now the new constraint is that the data type has to be subtractable. And once again we can go ahead and try this. We can add E, which is a int64, and F, which is an int64, and we can go ahead and simply print this as well. Now, as you probably have expected, this will work. Boom. So we go ahead and run this, and we should see it print 10. So that's really amazing. One more thing is that right now we are inferring the data type. So we don't have to specify which data type this is, but sometimes you need to do that, and we will get into that later. But the syntax, if I want to tell this function about the types that are used, you use the same syntax as when we declare it. In front of the function parameters, which are here, you pass in the type parameters. So in here we can pass in what data types we are using. In this case we are using float32, and you only need to pass in 1, because remember we say that capital V is of data type subtractable, and since both of our variables are V, you only need to pass in 1 data type, because remember you can't mix them, not yet. But the compiler will tell us this is unnecessary right now, because it really is, it can just infer this. But for the fun of it, we could also do, just so you will see. Alright, now we can't. Let's skip that, my bad. I just wanted to show you that sometimes you can insert multiple constraints. Basically that's what I wanted to show you. You're not limited to one constraint, you can have multiple constraints if your function needs that. And then if you had multiple constraints, you would need to pass them in here. We will actually have a showcase for this later. So let's move on. So one more thing I want to show you is that sometimes you have aliases for data types. So imagine we have a type called my own integer, and it's an alias for int. Now I wouldn't be able to do this. Now this won't compile or work. As you can see, the subtract will start complaining that my own integer is not subtractable. And you see that it mentions that we can use a tilde. Basically, derived data types are not included by default. So my own integer is derived from an integer, and it will work like an integer unless we add more features to it. But what if I want to support it? You could add it here to the constraint, but you can also add the tilde character like this. Now any data type that derives from int, int32, float32 for instance, will be allowed to be passed into the function as well. They will now be subtractable because we put the tilde here. So that's one thing that you might notice in other code bases, and when you notice them, think about it. It's just to allow derived types to also be allowed in the generic constraints. So we have covered generic functions. It's time to cover generic types. So we want to create a type that can store our results, and this type is going to be a slice of values. And what we basically want to do is we want a type called results, and we want it to be a slice of our values, so a slice of t, but t isn't defined because we need a type parameter. So once again, you add the type parameter after you define the type here, and we say that t is a type of subtractable. Now what we have done here is that we have created a slice of results that are subtractable. So we can hold any value that is subtractable. Let's take a look at how we start using it. So let's remove the my own integer. I have removed it, and I removed the results from it. So we have results from int and we have results from float32. So if we want to use the newly created type, which is a generic type, we will create a variable that is of this type. So we create the variable and we say that the variable is a results data type. Now remember that we need to use the type parameter. Now we have the type constraint, which is subtractable, and subtractable has the constraint that the data type has to be an integer or a blah 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 blah. Right. So we also, when we initialize the result, have to tell it which data type we are using. So we are using the data type int for this case. What we can do then is we can say that result storage equals append result storage, and we want to append results. Now you cannot add result float here, because result float is a float, remember. So subtract outputs a float because the input data types are floats. So what you do when you create the results slice is that you have to define the type, which has to be any of the subtractable data types. But you can only hold the value of the data type that you have used when you initialized it. I hope that makes sense. So if we wanted to store the floats, we would need a data type 32. Now we can store the floats here. So basically you're still limited to one data type, but you can use the same data, you can use the same struct for storing them. Now this still reduces the amount of code you need, because otherwise you may want a slice for the integer results or depending on what you want to store. But now you can still store using the same type multiple different data types. I'm really trying not to confuse you, but it's sometimes it's hard. So you might be wondering why you can't pass in subtractable here. And subtractable you can't pass in because it's an interface that contains a type constraint. So you can only pass in the data types that has to fulfill the subtractable constraint. So what if we really want to store them in the same? What you can do is that you could actually update this. So instead of subtractable, you could use any. Any is a new keyword added in 1.18, which is an alias for interface. Now it would be exactly the same thing to put in interface here. but it's shorter and looks better, so you can pass in any. And if you did this, then you could actually pass in any here as well. Now, how you can add all the data, result float, but I really don't know the use case, because you would now need the type switch again. Basically, when you start using it, you would need to check that if it's a float or not. There's also one more keyword added other than any, which is comparable. And comparable basically is any data type that can be compared using equals equals and not equals. So those two keywords you will probably see popping up in code bases, and it's good to know what they are. Now we have covered generic functions, generic types, and single constraints. It's time to cover multiple constraints and generic structures. So we will be creating a function that accepts a interface first, and we will trigger methods from said interface inside. And I'm going to go ahead and erase, let's keep the subtract, but let's erase everything in the main function and the results, and we will keep the subtract as well. So I'm going to go ahead and create our interface, which is movable. So any object which can move will fulfill this interface. And we will be having a generic function which accepts the movable type constraint, and we want to say that anything that is passed in as a movable, we will also accept meters, which is the distance that it will move. So using the object we can now move him, and we can pass in meters. So we have a movable interface, and whenever we get inserted into the function, we will also take the meters and pass it. Now we need something to actually implement this, so I'm going to go ahead and make a few very easy structures. So one is the person structure, and the person will have a name, and we will also have the car structure, and it will also have name or brand, but name. And our person will also have to implement the interface, so we're saying that person can move. And what we will do is basically print out that he moves. He moved a distance, meters. And we will add the name, and we will add the distance he moved. Now I will copy paste this and do the same thing for the car. I'll just switch the values here. And he moves, and it moved 4 meters, so it's basically the same. Now we will also add in the main, so we can actually see that this runs. So we will initialize a person, we will initialize his car, which is a Ferrari. That's amazing. Now we can move either one of these ones. We can move the car and the person, and if I go ahead and run this, we will see that John moved and the Ferrari moved. Why the car is moving further than John, I don't want to speak about it. Now still we're only accepting a single constraint, which is an interface. But we can actually accept multiple constraints, and the way you do this is the same way you do when you accept multiple function parameters. you can accept multiple type parameters. So let's also say that we want to have S be a generic, because we don't know if it's float meters or if it's int meters. We want that to be decided by the unit that moves. So we will have to accept a generic value for the meters. So let's say that meters is S. Now I will also want to accept the distance that we move, because I want to calculate how far it is to our destination. So the move function will return an S as well, because it will return the distance that is left to the destination. And once we now can do that, we can return the distance by subtracting distance and meter. And since we changed meters to be an subtractable data type, we also will need to make some modifications, because right now you will see it complain that we can't use S constraint because move wants a integer. So we need to make sure that this happens, and we can do that by changing move to be a subtractable value. But that's not all. We also need to make sure that the move interface accepts subtractable. Now let me just make sure that we are moving. Yes, and we have changed. Okay, that's everything. So the subtractable data type is accepted, and we now move meters, but we don't know the data type yet, so we will have these syntax errors, but we will solve them soon. So we can accept any object that can move, and we can also calculate the distance left regardless of if it's a person or a car, and regardless if it is in floats or integers. But it won't really work yet. There's a final piece to this puzzle, and it's called generic structures. So the problem right now is that we have an interface that accepts move, and move accepts a subtractable data type, but we don't really know what subtractable is, so that needs to be applied. And we can do this by adding to the interface that, again, a type parameter we add that is of the constraint subtractable. So now we say that movable accepts a type argument which will be any of the subtractable data types, and it will be able to move by that distance. So once we have done this, we also will need to change a few more things. So let's solve, it's actually complaining right now, and let's see why. We are moving, oh yeah, so you should not pass in subtractable here, we should pass in S, because S is of type constraint subtractable. So yeah, change that to move S instead. My bad. But now we have changed the interface. The interface is no longer simply that you have to move S, because how will the person here know what S is? As you can see, it's complaining. Person doesn't know what subtractable is, because the data type here is not defined in the type parameter. So we will actually need to change the person here to accept the type. So we can go ahead and make this by stating that person is a generic structure, because person accepts a type argument of subtractable. Let's go ahead and add that to the car as well. And once you have done that, we will also need to modify a few other things. I hope this makes sense now, because you're saying that there's a person structure, and that structure accepts a type argument, the same way we do here. And when you define move here, we say that we want to move by a subtractable amount. But again, the move function doesn't know what subtractable is. It has no idea. But you might ask yourself, why did we add subtractable here? Didn't we just tell person what subtractable is? And we did, but this move function is applied to a regular person. And a regular person does not exist. We only have a generic type. So you need to specify here that this is a generic person which accepts the S parameter. And we can go ahead and do the same thing for the car. The car should not accept a subtractable meters, it should accept an S, and S will come from when we declare the person. We will very shortly look at this, or we can fix this now. So we have a generic person which accepts a type parameter. So when you create person, it will complain that this is generic, and you need to initialize the data type by using a type argument. So you can go ahead and again add with the brackets the type that you want to add. So once a human moves, or a person, we want it to be floats, because they can move small amounts. And the car wants to be an integer. So let me recap on what's really going on so you follow along. The person is a generic type, which you can see here, and the person accepts a data type which is subtractable. So we have to assign a data type that person is going to use. So once we have this, we can actually fix the last thing. And let's see what it complains about. We don't have enough arguments to move because we added a few arguments. We added the distance. And oh yeah, let's see. So it actually complains here as well, because move does not accept movable anymore. Movable is a generic interface, so any structure that accepts a type argument of subtractable and has the move function. So we need to say here that the movable is subtractable. Oops. What's going on with my ID? Subtractable. Oh crap, sorry. So now you can see that movable is an interface that is generic, and we accept the subtractable into it. So now we can add the distance. So let's say we want to see how far John has. So let's go ahead and add some things. So John has a distance to his job, miles to destination, which is, he has 100 miles to his job. And the distance left we can get by moving him, and we can move the car, and we can move miles to destination, and we can say that he is now moving 95 by, let me just remove that. So we are moving the car by, we have a distance of 100 and we are moving 95. So let's go ahead and print that just to see that everything is running. We have distance left. So if I run this, we should see P declared and not used because we're not using the person. That's correct. And let's just print him so we can avoid the compiler complaining. So the Ferrari has moved 95 meters. That should be miles, but yeah. And we have 5 left. So everything is working as we expect it to. Yeah, it will complain because we need. I'm just printing. Let's change that to V. So we fix the compile of that. Okay. Now once again, we are having a movable interface that accepts subtractable, and we accept S as an input to move, and person is a generic structure because person accepts a type argument or a type parameter. So we can actually use the move function for both person and for car, which is great. Now, a small hiccup, and I mentioned this before, that sometimes you need to assign the type arguments here before you invoke the function. And we can view this when we use the person. So the person is using float 64s. So distance left is a integer right now because move will return the inferred subtractable data type, which is int. So let's convert it to a float, and let's move him the last of the distance. So he's walking from his car to the parking lot, basically. Now this won't work without adding the type arguments. So you need to say that the first input in the function should be a person with the type argument of float 64, because that's how we initialized him, right? So basically we're telling the move function that the input you're receiving is a person of float 64. That's the data type that you're receiving, and that's the data type you should be using. And next, you're receiving float 64s. So both the distance left and the distance we move are float 64s. And we can now again print the new distance. So we will run it, and we will see that we have arrived at our destination. Now you can actually remove these type arguments. It seems you don't need them anymore. I think this has to do with the latest update. I'm using Go 18.1, and I think they removed and improved the inference a lot. So this is generic structures. I hope the generic structures made sense. I know we really speeded it up and made it a lot more complex, but I hope you see the beauty of it, because we can move the person, we can move the car, and we can change the data type, and we can really, I mean, if we were going to do this without generics, it would be much more code, I believe. So yeah, hopefully you understood everything. So Congratulations, you're finally a master of generics. I hope you feel that you could follow along, and if you didn't, I know it was a bit hard here in the end, and feel free to leave advice on how I can improve my channel. I always want to improve, and I really hope I will see you more. And again, you can view my video on all the changes in Go 1.18, and one of them is fuzzing. And if you're not familiar with fuzzing, I recommend viewing my video and learning how to create test data to your unit tests and really finding those hard to find bugs. So I will see you around.